Chemistry is the study of matter, the 118 elements that make up everything we see. It is also the study of change, as atoms form bonds to create compounds, and compounds react with other compounds to make new substances from old. It is the bridge between the other sciences, holding everything together. You are about to enter a world so small that gravity no longer matters, and we must turn to other forces to explain its existence. This is chemistry.
Part 3. Electron configuration and periodic trends. In Part 2, we learned that each row of the periodic table represents a new electron shell or energy level in an atom. In this part, we will be a little more specific and cover energy sublevels. I'm sorry this one might be a little boring, but after we grasp this, we can move on to the exciting stuff. The number of electrons that can exist in a shell follows a simple equation. Let n equal the energy level number, and the equation is simply number of electrons equals 2n squared. This means that the first energy shell can have 2 electrons, as was shown in the last video. Second can have 8, the third can have 18, and the fourth 32. However, these higher energy shells are filled in an unusual way, and to understand this we must look at the energy sublevels. The sublevel with the least energy in any shell is the S sublevel. The S sublevel contains one orbital. In every orbital there can be 2 electrons, one with a positive spin and one with a negative spin. The first energy level only has an S sublevel. The second energy level, however, has both an S and a P sublevel. The 2p sublevel has more energy than the 2s sublevel, but not as much as the 3s sublevel. P sublevels have 3 orbitals, so they can hold 6 electrons. The third energy level looks just like the second, where the elements first fill up the 3s orbital, and then the 3p orbitals. As mentioned before, the third shell can accommodate 18 electrons. However, the 4s orbital actually has lower energy than the 5 3d orbitals, which account for the other 10 electrons in the third energy level. Therefore, we see 2 elements in the fourth energy level before the 3d electrons are filled in. After the 4s orbital is filled, electrons are added to the 3d orbitals, and elements in this position are known as transition metals. The transition metals contain many of the elements we typically think of as metals, such as titanium, iron, copper, silver, and gold. After the 3d sublevel, we continue with the 4p, then 5s, 5d, 5p, and 6s. This is when it gets complicated again. After the 6s sublevel, we have a single electron put into the 5d suborbital, but then we start filling up the 4f sublevel. There are 7 f orbitals, so it takes 14 electrons to fill this sublevel. To prevent the periodic table from becoming too wide, we just take these elements and throw them below the table, but really it should look like this. After 4f we have 5d, then 6p, followed by 7s, 5f, 6d, and 7p. These are all of the elements that have so far been discovered or made. Still awake? Let's get to some more fun stuff, periodic trends. Because of the organization of electrons, elements in the same column have the same valence electron configuration and have similar chemical properties. Physical properties include things like melting point, boiling point, color, etc., while chemical properties deal with how things react. The first column of the periodic table contains those elements with only a single valence electron. Other than hydrogen, which can be considered to be in its own category, the elements in this column are known as alkali metals. They are all soft metals with a low melting point, and they are very reactive.
To demonstrate this, I will place a small amount of potassium metal in water. You will see that it instantly reacts, and will float on the water as well. Next are the alkaline earth metals. These are less reactive than the alkali metals, but can still pack a punch. Magnesium, for example, burns a really bright white. Here I will place a small sample of strontium metal into water. You will see that it reacts just like potassium, except much less violently. It bubbles in the water, creating strontium hydroxide, which is not very soluble, so it comes out of the water fairly quickly.
Transition metals are what we typically think of as metals, and I will explain the chemistry of transition elements more in later videos, after we build up a bit on the basics. The F-block metals, known as rare earth metals, are generally fairly reactive, which is why they are never found in free form in nature. They are all very much alike, and because of this are hard to separate. After the transition metals, we hit what looks like a set of stairs in the periodic table. This separates metals from nonmetals and is the result of competing trends that I will mention shortly. Along this staircase are the metalloids, elements that have both metal and nonmetal characteristics. They can be somewhat metallic in appearance, but do not usually form ionic bonds like most metals, and conduct electricity only under certain conditions. The third column from the right contains the chalcogens. Other than oxygen, all of the chalcogens react with hydrogen to form smelly gases. Hydrogen sulfide, for example, gives the familiar rotten egg smell. Oxygen is a bit of an oddball in this group, as will be discussed when we get further into bonding and intermolecular forces. Following the chalcogens are the halogens, which are extremely reactive nonmetals.
So here I have two different halogens. I have chlorine and I have bromine. Now chlorine is a gas at room temperature. So in the video you can see this pretty much looks like an empty glass ampule. Bromine is the sort of brown liquid. Now both of their vapors are visible. And I can show you best against a white background here. So chlorine sort of has a very faint green. It's hard to see in the video, but if I give it end to end, you can kind of see a faint green color. And then bromine, much more visible, is a very bright orange-brown. Iodine's vapor is purple. It is harder to show because iodine is a solid at room temperature, so I would have to heat it up.
They are diatomic molecules, meaning they form a two-atom molecule with themselves, so they exist as F2, Cl2, Br2, and I2. Last but not least, we have the noble gases, which have a full valence shell and do not easily react. So metals are on the left, and nonmetals are on the right of the periodic table. In general, there are some other trends that also exist. Elements toward the top and right of the periodic table have a higher electron affinity, which is the amount of energy released when an atom gains an electron to become an anion. First ionization energy also increases, which makes sense because the more energy released by gaining an electron, the more energy lost by losing an electron. Atomic radius, a measure of the size of atoms, is greatest toward the bottom of the periodic table, as would make sense because those atoms have more electron shells, but atomic size is also greatest on the left of the periodic table. Why? Think about it. As the nucleus gets heavier and more charged, it holds the electrons tighter. However, if you look at a chart of atomic radius, you will see a spike at the beginning of each sublevel. Thank you for putting up with this really long and monotonous part of This is Chemistry. The next part will deal with some basic compounds and get a little more exciting. See you next time.